Welcome back to this next video in which we are working on deriving the Taylor series. So we have started a fresh new board and I'm going to begin this fourth part of the video just by reaffirming the concepts that we went over in the previous video, because that is so important, because that's the crux of it all. So let's draw a picture. So we'll have our graph here, our y-axis and our x-axis, and we'll have our function f here. So remember, what we saw in the previous video is that if you know the value of the function at some point a, so remember whenever we're making these series, the Newton series or the Taylor series, we're always going to start the series at some value of x, and we're generalizing that and just calling it a, so it could be anywhere along the x-axis. So if you know the value of the function at a, and you know the value of the higher derivatives at that point a, then that tells you stuff about the function in the future. So for instance, if you know the value of the function, so obviously if you know the value of the function at a, then you know something about the function. You know at least that it goes through this point here, the y value f of a at the point a. If you also know what the first derivative is at that point a, and remember we're talking about first derivative in terms of finite derivative, and we're working with some finite difference s, and again we're generalizing here. S could be any value. It could be 1, it could be 2, it could be 3, it could be negative in fact, but obviously that would be going backwards. That would just be derivatives going the other way instead of going forwards, and we're only going to talk about them going forwards. You can talk about them going backwards. I mean, there's no difference between going that way and going this way. The principle is exactly the same, but we're, just to keep it simple, we're just going to think about it being a positive value, and of course it can't be 0 either. So s again is, we're working in the general case, but if you want a concrete example, you could think of s being equal to 1. That's a nice example. So if you know the value of the first derivative at that point a, that then tells you what the value of the function is going to be at a plus s. So if you go forward by the difference from the point a, so you go to a plus s, then if you know these two pieces of information, then it is set in stone instantly what the function must equal when evaluated at a plus s. So these two pieces of information immediately set in stone what the function must be at a plus s. And then it goes on, you know, if you have the second derivative value at the point a, then that tells you what the value of the function must be at the point a plus 2s. And of course you need the pieces of information that went prior, so it's this, and this. All of those together then allow you to work out what the function must be at a plus 2s. And then the third derivative gives you a plus 3s, the fourth derivative gives you a plus 4s, the fifth derivative gives a plus 5s. Of course it gets more and more complicated to actually work it out, what the value of the function must be at a plus 5s from all the derivatives. But in principle you could. So the derivatives, the values of the derivative at a point, then set in stone what the value of the function is going to be in the future. So here is the crucial idea. Suppose now that we know what all of the derivatives are going to be equal to at this point a. So suppose I know the value of infinitely many derivatives. So we're just now going to say f to the power of n difference s at a. Suppose I have every single one of these numbers, and of course some of them might just be 0. You know, if we took for instance the function f of x is equal to 2x plus 1, that's a function, we can draw that, oops, so it looks something like that. If we want to take the first derivative with respect to with a difference s, then that is just going to be, let's work it out, 2x plus s plus 1 minus 2x plus 1 in brackets. So the 2x's will cancel there, the 1's will cancel, and you'll just be left with, and it's all divided by s of course, you'll just be end up with 2, just as it would be in the case of a normal derivative. So for linear functions, the finite derivative is exactly the same as the continuous derivative, and of course it's obvious why. There's only one gradient that any little triangle is ever going to have on here. No matter what the difference, the triangle is always going to have the same gradient as the line, which is 2. And then, of course, if you take the second derivative of that, well, the second derivative of a constant is just 0, and then the third derivative would just be 0, 0, 0, 0, 0, 0, 0. So the infinitely many derivatives after the second derivative and beyond, they're all just going to be equal to 0, no matter what point you're at and no matter what difference you choose. So yes, it might be the case that they don't have very interesting infinitely many derivatives, but every function, these functions can in principle be differentiated infinitely many times. So supposing we now know for our function here what the value of all the derivatives are at this point A. So going on for n is equal to infinity, so this goes on and on, n is indefinite, so we can imagine that n is equal to infinity. So we know infinitely many derivatives evaluated at that point A. Then you can imagine that what that sets in stone is what the function is going to be forever, basically, so we'd know not just what the value of the function is at the value a, but we'd know what it is at a plus s, we'd know what it is at a plus 2s, a plus 3s, a plus 4s, a plus 5s, a plus 6s, etc, etc, etc. So we'd know what the value of the function is going to be at a plus ns. So if we don't set a ceiling on how high we take n, then we're going to know what the value of the function is forever, basically, or at least at those points. Of course, you can say, well, we don't know what it's going to be in between, in the difference s, but you can imagine that if we were to create a function that also had exactly the same values of the derivative at that point a, then as I drew before with a picture, it's got to look something like this. So here is our red line. It would have to go through all the same points. It would have to intersect with our white function at all of those points until we get to a plus ns. And if n was allowed to go to infinity, then it would have to be going with it infinitely onwards. And that's the principle behind how we're going to create the Newton series for a function. We're going to say, let's try and create a function that's going to have all the same values of the derivative at this point a as our function f. And then it must be the case that it goes through the same points as the function f at all these values a plus s, a plus 2s, a plus ns. And if it's that similar to the function, you can imagine that all these bits in the in-between bits are going to be very, very close to the function f. And what we could even do is we could imagine then shrinking our s down, the difference down, so that would make these gaps in between the points where there are going to be intersections of the two functions smaller and smaller. So, if you were to halve s, now the function is going to have to intersect to all these little points here, and you can make s smaller and smaller and smaller, and as you take the limits as s approaches infinitesimal amounts, that's when the Newton series becomes the Taylor series. So it's very, very clever. So let's now actually construct a function that would have the same values of the derivative of higher and higher numbers of derivatives as our function f. So we're now assuming then that we have our function f of x, we have our point x is equal to a, and again we're working with a general point, so we're just calling it a, and we now know the value of the function at that point a, we know the value of the first derivative with a difference s, and again we're leaving s general, so s could be any one of these forward differences. We know its value at a, we know the value of the second derivative, evaluated at a, etc. And I'm going to now say we know the value of the nth derivative evaluated at a, where we're not going to set a ceiling on how far n can go, and we're going to imagine that we know it we know it for infinity, basically. And indeed, for some functions, we definitely do. So for instance, this function here, we categorically know what the derivatives are going to be all the way up to infinity, because after a while they just become 0. So let's now work on how we can actually create a function that is going to have those same values of the derivative at the point a. And this is where it becomes really important to remember those beautiful functions that differentiate nicely in calculus of finite differences, i.e. the falling factorial functions. So I'm going to write this out because I don't completely know how to actually explain to you how to arrive at this. So instead what I'm going to do is just give you the answer and then explain how brilliant it is, and hopefully you'll see that. But I don't really have a good explanation for how you would actually see this without just it being a eureka moment in your brain. So I apologise for that. So we're going to create a function then, and we'll call this our approximation function. So I will, what can we call this? We'll call this f bar. So this is our approximation function that we're trying to construct to approximate our function f of x. It's effectively the series that we're trying to make to mimic this by making it go through more and more points analogous to this one. So firstly, we want it to be equal to the value of the function at the point A. So if we just make it equal to f of A, that's effectively our first approximation. So our yellow function at the moment would just be equal to this on the line. And okay, it's not a very good approximation of our function f, but at least it's right at one point. It's right here. Now what we want to do is make it right at the point a plus s, and to do that we need to make sure that this function is going to have not only the same value of it's not only going to have the same value of the function at a, but it needs to now have the same value of the first derivative at a. Now, if you differentiate what we've got at the moment, this just goes to 0. So at the moment, the first derivative is equal to 0. So what we're going to do is we're going to put in a function that, when differentiated, will give us and evaluated at x is equal to a, will give us the value of the first derivative, and that is going to be by adding on the first derivative evaluated at a, which is a number that we know, that's that number from here, and then we're going to times it by x minus a, like so. So what have we now got there? Let me explain why this works so brilliantly. So firstly, when we add on more terms to our approximation, we have to make sure that it doesn't break what we've already got. So we have to make sure that this additional term isn't going to change the value of our approximation at the point x is equal to a, because this was perfect at the point x is equal to a. It was matching the function perfectly. And that is why we're timesing this by x minus a, because now if you stick in x is equal to a here, this obviously goes to 0, and therefore this term is lost, and therefore the value of our approximation is still just f of a at the point x is equal to a. So it's still going through that point there. Now, if we differentiate this with the difference s, well, we know the basic rules of differentiation in calculus of finite differences. That's just going to give us this as the answer. You know, if we differentiate this, that will go to 0 because it's just a constant term. And then we've got x times this minus a, which is just a constant term, remember, times this, so that bit will be lost. So you'll just end up with the derivative of f prime of sa times x, which is just f prime of f prime evaluated at a. So that means that the derivative of this, evaluated at a, will be equal to the correct thing. So effectively, what our approximation has now become is the line, like so. It's become a linear formula. So now it's right not just at the point x is equal to a, but it's also right at this point a plus s. And now we want to make it right further along, so we want to make it right at a plus 2s, so we now need to add something on that doesn't break what we've already got, so we need this to remain equal to this at the value a, and we need it to remain the case that the first derivative is going to be equal to this. But we now want to add on a term that will mean that the second derivative is equal to our second derivative here, because if we do that, then we know that our function will have to now go through, it will have to match our function f at the point a plus 2s as well. So what are we going to add on? Well, again, this is the point that I'm just going to have to write it down and then show you how it works. So we're going to have our second derivative evaluated at a, which is just a number, remember, and then we're going to want x minus a, and then we're going to want x minus a, and then it's effectively the falling factorial with the difference of s now. And this time we're going to divide it by 2 factorial, which of course is just 2. Now let me explain why this is going to work. So, firstly, let's make sure it hasn't broken the first bits. So we want it to be the case that our approximation function is still just equal to f of a when you evaluate it at x minus a. Well, put in x is equal to a here, this goes to 0, and oh look, we've got x minus a over here as well, so this goes to 0. So both of these terms are going to be equal to 0 when x is equal to a, so the value of the function at x is equal to a is still just going to be f of a. So good, the first bit hasn't broken. Then let's take the first derivative of this, and I think now we'll actually have to write this out. So if we take the first derivative of our approximation function with a difference s, then it's going to be equal to, so this function, this is going to be lost because this is just a constant term, so that'll go to 0. This bit we've already discussed, it will go to f prime evaluated at a. And then the bit over here, well, we're now going to take a derivative, and look, we've used this beautiful falling function which we know differentiates nicely. So let's just prove it once again, because obviously, when we discussed it previously, we discussed things like x minus s, x minus 2s. We've got the same thing here, it's just we've got this x minus a instead, which, you know, I hope it's intuitive to you that that's not going to make a difference, but let me just prove it to you, because it's effectively just like substituting a slight translation of the x-axis in for here. This would have been the point where it would have been nice to, you know, have proven the chain rule, because then we could easily show this, but let's just show it anyway. So let's differentiate that with a difference of s, so it will be equal to, this is just a constant term, so we can pull that out, and then 2 factorial is also just a constant term, so let's then just differentiate the bit inside. So it's going to be x minus a plus s, x minus a, so that's this bit evaluated at x plus s, and then we're going to subtract off what it is at x, which is x minus a minus s, and then divide all of that by s, like so. My bracket was lost there. So, obviously factor out the x minus a, and then we get x minus a plus s minus x minus a minus s, all times by x minus a, and then all divided by s. Cancel this, so the x's cancel, the a's cancel. So this is why the a's don't matter, look, they cancel out like this beautifully. And then we just end up with 2s there. So this is going to be equal to 2s x minus a over s. So it just ends up as 2x minus a. So effectively, if you want to use the sort of notation that we invented, what we have here is x minus a to the power of 2 falling, where the difference is s, and then we've just differentiated that with a forward difference of s, and we've ended up with 2 to the power of 2 times x minus a to the power of 1 falling, which is just to the power of 1. And that is why we have put the 2 factorial here to cancel with the 2 that we get from differentiating this. So what we're actually trying to do here, we were trying to differentiate this so that we could work out the first derivative now of our approximation. So all of this term just becomes the second derivative evaluated at a. The 2's are going to cancel, so this 2 here cancels with this 2 here, and therefore you're just going to end up with x minus a. And you see how brilliant that is now, because look, here's the first derivative of our approximation function, And if we stick in x is equal to a here, this obviously just goes to 0, so this term vanishes, and therefore the first derivative evaluated at a is just going to be equal to this, which is exactly what we wanted, because we now know that our approximation function here has the right value of the first derivative at the value x is equal to a. And then finally, we just want to check that it's got the right value of the second derivative, so if we just differentiate further, so if we take the second derivative of our approximation function, well, we're just differentiating this now, so that's a constant term, so that goes, and this, we know that if we differentiate that, we just end up with the factor here, which is the second derivative evaluated at a. So yes, obviously, when you stick in x is equal to a, there is no x term here, it's just constant, so it is going to be equal to this. So, that approximation that we have created there, this here, is going to be right for the first derivative, the function's value, the first derivative's value, and the second derivative's value, and therefore it is now, it's more difficult to draw what it's going to look like now, because obviously it's going to have squared terms in, but it's going to be right, it's not going to be a linear function anymore, but it's going to be right at this point, this point, this point, and this point, so a plus s, and a plus 2s. So we've got it, it's becoming a better and better approximation is what I'm saying. And now it's not necessarily going to be right in the bits in between, so all of these points in between, it might be completely wrong, but at least it's going to be right at these points, and it's become a better approximation than the two first ones we had, which was the straight line, and then this straight line. And then we can go on. We can create a function that's going to have the correct third derivative, and then it's going to be right at a plus 3, and this again will be the last one that I actually write out. So just for the interest of actually making this make intuitive sense, let's try writing the one with the third derivative in now. So our even better approximation function is now going to be everything that we've already got, so f evaluated at a plus f prime evaluated at a, x minus a, plus f double prime evaluated at a, and then remember that what we've got here is effectively x minus a to the power of 2 falling where the difference is s, like so, and then over 2 factorial, which is just 2, and now the final term that we're going to add on is going to be, hopefully you can work it out just with intuition now, the third derivative evaluated at a, and then we're going to have x minus a to the power of 3 falling where the difference is s. So it's going to be x minus a minus s, and then x minus a minus 2s there. And then it's going to be over 3 factorial. So why is this going to work? So it's going to have the right value of the function, because when you stick in x is equal to a, this one's got an x minus a, this one's got an x minus a, and this one's got an x minus a, so all of the others go to 0. So the value of the function at x is equal to a is going to be correct. When you take the first derivative, we'll do that and show you exactly why it works. So this bit obviously vanishes. This bit, the second term, is just going to become the first derivative evaluated at a. The next term, we know how x minus a falling differentiates, because we're differentiating it with a difference of s, which is the correct, it's compatible. So we know that that's going to become f, the second derivative evaluated at a, and that's going to be x minus a to the power of 1 falling, where the difference is s, times 2, and then of course that cancels with the 2 underneath. And then if we differentiate this next one, I'm not going to write it out in full, but look, we have got here x minus a to the power of 3 falling, where the difference is s. We're now differentiating that with a forward difference of s. So that becomes equal to 3 times x minus a to the power of 2 falling, where the difference is s. So we're going to get the third derivative evaluated at a times 3x minus a to the power of 2 falling, where the difference is s, over 3 factorial. Now, so if you evaluate that at x is equal to a, then of course this has an x minus a in, because 1 falling is just x minus a, so this term goes to 0, and this one over here has also got an x minus a in it, because it's now equal to x minus a minus s, which is x minus a to the power of 2 falling, where the difference is s. So it also goes to 0, and therefore the value of the function at the value of the first derivative of the function at a is going to be correct also. Let's now check the value of the second derivative. So we're going to differentiate it again now. So this is a constant term, so this vanishes. The 2's here cancel. This is going to become, because this is now just a linear term, this is going to become just that value, which is the second derivative evaluated at a. And then the final term, we've now got x minus a to the power of 2 falling over here. So when we differentiate that, we're going to get, we've already got that 3 there, but we're now going to get a 2 as well. So then times the third derivative evaluated at a, and now it's x minus a to the power of 1 falling, where the difference is s, which of course is just x minus a, and over 3 factorial, which of course is just 3 times 2 times 1. And now you understand why that factorial was there. It's there to cancel with these numbers that you're getting from the differentiation of the falling factorials. So to cancel this, it just goes to now the third derivative evaluated at a times x minus a to the power of 1 falling, which is just x to the minus a. So of course when you stick in x is equal to a here, this goes to 0, and therefore you just end up with the second derivative evaluated at a. So correct, the function, the approximation does have the right second derivative at our point x is equal to a. And now we just need to check that it has the correct third derivative. So if we take the third derivative of our approximation function, well, this is a constant term, so this vanishes, and this bit over here is just going to differentiate to the third derivative evaluated at a, and therefore of course when you stick in x is equal to a, there is no x in this formula, so it's just going to be equal to this. So now our approximation function has the correct value of the function, the correct value of the first derivative, the correct value of the second derivative, and the correct value of the third derivative, and therefore it's going to go through not just it's not going to be correct not just at a, it's going to be correct at a plus s to a plus 2s, and then a plus 3s here. And you could continue in this manner. If we had infinitely many derivatives at the value x is equal to a, then we can create a bigger and bigger approximation that is going to become more and more accurate. More and more complex, but more and more accurate. So, the general formula then that we are creating here, which is the Newton series for a derivative where the forward difference is s, is going to be our approximation function. And now I will continue putting the bar over it. It's an approximation of our function f, although as we're going to see, you know, if it's going on infinitely, then it's going to become closer and closer to the real thing, so we might just drop the bar and start calling it f. It's going to be equal to the sum from, we'll use r is equal to 0 to infinity, so we can go on indefinitely, and then we're going to want the rth derivative with this difference s evaluated at a, and we're agreeing then that the 0th derivative is just the value of the function, so that first term where r is equal to 0 will be this one, when r is equal to 1 it will be this one, r is equal to 2 it will be this one, r is equal to 3 it will be this one. And then we're going to want over r factorial, and again that works for this term because when r is equal to 0, 0 factorial is agreed to be 1. For this one, when r is equal to 1, 1 factorial is just 1, so it doesn't matter. This one is 2 factorial, this one is 3 factorial. Excellent. And then we want here x minus a to the power of r falling where the difference is s. And that is the Newton series, effectively. This is not how you will see the Newton series. As I've warned you throughout this video, I'm using non-conventional notation here, but this is effectively equivalent to the Newton series. If you go on Wikipedia and look up the Newton series, you'll see it very different to this, but it's the same thing. This is this is what we've constructed, basically. It's the exact same ideology, the exact same idea. Right. And now, so just to explain to you what this is going to do then, once again, just to drill it into your head, if we have our graph here, and we have our function f, the higher and higher this goes with terms, if this was to go on infinitely, it's going to effectively have to agree with the function for infinitely many points in the future. So remember, if we imagine just putting in n here instead of infinity, where n is some natural number, then this approximation function has to be correct at the point a. It will then be correct at the point a plus s. It'll be correct at the point a plus 2s, and onwards all the way up until a plus ns. So however far you take this series, it's correctly approximating the function for more and more points. And you can imagine if it's going through all of these points in agreement with the function, the more and more you force it to go through, the more and more similar it's going to have to become to the function. And you can imagine that if it were to go through infinitely many points in agreement with our function f, that surely it must be so close, maybe it is even equal to it. And that's the concept of the fact that this might well truly become the function as you extend this upper limit here to infinity. Now, even better, we have done this for a general difference s. Now, it might be difficult, even if we say were to make our function, our approximation, agree for infinitely many points in the future, it might be difficult to prove that it converges in all the points in between here. And in fact, you can very easily come up with counterexamples where it wouldn't be the case. So for instance, you could create some, if you had your function f, so remember this function that we're trying to approximate, we could create a function that had the same values of f at all these points onwards from a with a difference of a multiple of s. You can imagine that we could create something like this. We could have some sort of periodic thing going on where it's similar to f, but it's not going to actually equal, even though it equals it at all these points, it's not actually going to be equal in the gaps between. So you can imagine that it might not be the case that this truly converges on the function f as you extend this up to infinity. However, here's the next genius thing. We can make this difference s smaller and smaller and smaller, which effectively shrinks these gaps in between these bits that we know are going to be right. And if we now think about this in the limit as s approaches 0, so making the difference infinitesimal, that is where this approximation is going to become the Taylor series. So let's now do that. So we're going to take the limit as s approaches 0 of our approximation function here, the Newton series effectively. So let's do that. Limit as s approaches 0 of this great big sum of the rth derivative evaluated at a over r factorial x. And in fact, this is the point where it's going to be easier to write out the falling factorial with a product. So we'll put this in, and it's going to look hideous, but remember it's the product, and we'll use from I is equal to 0 to r minus 1 of, and then it's x minus a, minus I, like so. I believe that's correct. Wait, we've missed out the s. Minus is. Yep, so that's equal to what the falling factorial function is. So when I is equal to 0, you get x minus a, and then you're going to multiply it by when I is equal to 1, which will give you x minus a minus s, and all the way up to I is equal to r minus 1, which will give you x minus a minus r minus 1s. Good. So now let's do this. So of course, the limit of a sum is just the sum of the limits. So take the limit inside the summation there. So r is equal to 0 to infinity of the limit as the half derivative with a forward difference of s, where s approaches 0. Well, of course, that's just going to become the normal type of derivative. So when we're taking the limit as s approaches 0, these finite derivatives just become the normal derivative. So that's just going to now become the r derivative from normal calculus. R factorial is just a constant, so it's not going to be affected by the limit process. So now we just want the limit as s approaches 0 of our falling factorial function. So I is equal to 0, r minus 1, x minus a minus is, like so. Well, in the limit as s approaches 0, you can effectively just forget about this. So this is now becoming 0. So this effectively just becomes the product from I is equal to 0 to r minus 1 of x minus a. And now there's no I in there anymore. So for each I from 0 to r minus 1, this is just equal to x minus a. So it just becomes x minus a times x minus a all the way up to x minus a. And then how many times are you going to get that? You're going to get that r times. So just to give you a more in detailed explanation of what's happened there, remember that if we write this out in full, what this means is x minus a times x minus a minus s, x minus a minus 2s, all the way up to x minus a minus r minus 1s. Now, if all of those s's are approaching 0, well, they effectively just vanish because these are all just becoming 0. So all you're just going to end up with is x minus a times x minus a. How many times are you going to get it? Well, from this term to this term, we've got r minus 1 terms, but then we've got this term as well, so we're going to get it r times. So it just becomes, therefore, x minus a to the power of r. And then you recognise what we've got there is equal to the sum from r is equal to 0 to infinity of the rth derivative evaluated at a over r factorial x minus a to the power of r. Quod erat demonstrandum. There we go. That is where the Taylor series comes from. It comes from this Newton series, which is from the finite derivatives as you take the limit, as you make s smaller and smaller, and what does the series become as you do that? As you take the limit as s approaches 0, it becomes the Taylor series. And I hope that makes sense effectively what it's doing. If we make s smaller and smaller and smaller, the gaps are going to become smaller and smaller and smaller, and therefore you can imagine that this approximation function has to become more and more accurate, because with the Newton series, the fear is always that, yes, it's going to agree at all of these points, which are a, all of the points which are of the form a plus ns. It's going to agree on all of those points, but the fear is what's it doing in between each of these points. So what's it doing in between a plus 4s and a plus 5s? What's it doing in that gap of size s? We don't know necessarily, but if we make the gap infinitesimally small, which is what we're doing when we take the limit as s approaches 0, then we can avoid that problem, and that's where we come up with the Taylor series, which is the best approximation. It is better than a Newton series approximation, because the Newton series can be fooled. It may well be that the Newton series is just as good. In some functions it will be just as good, but it can be fooled because it has these gaps between the points where the approximation is going to agree with the value of the function. So thank you for watching this video. I hope you have found it interesting.